News agencies across the world are abuzz with headlines about a nuclear power plant plan for the moon. China and Russia have announced their plan to jointly build a nuclear power facility near the moon's south pole by the year 2036. This station will supply energy to the International Lunar Research Station, or ILRS, a project led by the two nations. The initiative is set to launch with the Chang'e-8 mission, scheduled for 2028. By 2035, all necessary equipment and materials will be transported to the lunar surface using super heavy rockets. The entire construction will be carried out by autonomous robots, and the system is being designed to operate fully without human intervention. While it may sound like the opening scene of a science fiction film, this development is quickly becoming a technological and scientific reality, one being taken seriously, with concrete steps already underway. On May 12th, Chinese President Xi Jinping and Vladimir Putin signed a historic agreement to formally begin cooperation on this lunar project. To fully grasp the significance of this moment, we first need to examine what kind of infrastructure is being planned, whether such a facility is truly feasible, and ultimately, why this cooperation is happening at all. But let me say this right now. Whoever controls helium-3 on the moon controls Earth's energy future. Why, you ask? Because it's estimated that the moon contains about 1.1 million metric tons of helium, and just 25 tons of helium-3 would be enough to power the entire United States for a year. Let's start with the basics. If you're planning to build a manned base on the moon, the first thing you need is continuous energy. That's precisely why this project begins with power infrastructure. One day on the moon lasts about 28 Earth days. During the 14 days of uninterrupted daylight, surface temperatures soar to plus 120 degrees Celsius. Then comes 14 days of darkness, during which the temperature can drop to minus 170 degrees Celsius. The bottom line is, solar panels alone won't cut it for a human outpost on the moon. To survive the 14-day lunar night, nuclear energy is virtually the only viable option. According to official statements, the process will begin with the Chang'e-8 mission in 2028. In fact, China has been planning this project well in advance. The mission aims to establish basic power and communication infrastructure on the moon, a foundational step toward building the International Lunar Research Station, or ILRS. According to the timeline, the first Chinese astronaut is expected to set foot on the moon by 2030. That's all the concrete information available so far. But it raises a central question. Is this project truly an achievable vision, or simply a symbolic show of strength against the United States? The first major challenge is clear: transporting materials to the moon. While details are limited, officials have confirmed that super heavy rockets will be used for this task. Because in a project of this scale, the most critical factor is the ability to deliver massive structures and heavy systems to the lunar surface reliably and efficiently. At this point, the global leader in super heavy rocket technology is SpaceX. Under the leadership of Elon Musk, the company's Starship rocket is capable of carrying up to 250 tons of cargo, and its fully reusable design offers an enormous cost advantage. Reportedly, a single Starship launch costs only around $2 million, though this estimate is for reaching low Earth orbit, not the moon. By contrast, NASA's non-reusable Falcon 9 rocket costs about $67 million per launch. Neither China nor Russia currently possesses reusable rockets, which places them at a logistical and economic disadvantage. Meanwhile, China and Russia are also active participants in the race to develop super heavy rockets. Both countries currently have conceptual projects in progress: China's Long March 9 and Russia's Yenisei, or Dawn programs. These rockets are projected to reach a payload capacity of around 150 tons. Although these systems have not yet reached the testing phase, considering both nations' prior experience with launch vehicles, it is technically feasible for these rockets to become operational by the target date. While no official details have been shared regarding the reactor's exact size, it is almost certain that a reactor capable of supporting lunar research operations will be selected. According to the International Atomic Energy Agency, a reactor with a capacity of 300 megawatts would not only provide energy, but also support vital processes, such as oxygen production and lunar soil melting. Therefore, the planned reactor on the moon would be considered relatively small by Earth standards. This makes a 300-megawatt modular system the most technically and logistically reasonable scenario. The planned 300-megawatt nuclear power plant for the Moon will consist of 4 modular units, each based on the NuScale power module design, producing approximately 77 megawatts each. On Earth, each module weighs around 700 tons, but the lunar versions will likely be heavier due to the absence of an atmosphere and the need for extra shielding and cooling systems against radiation. NASA has announced plans to begin testing such radiative cooling systems, though no clear updates are available at this time. The reactor's annual fuel requirement is estimated to be about 80 tons. Since there is no accessible water on the Moon, traditional cooling systems will not be viable. Instead, foldable radiative panels are planned, which could add an additional 200 to 300 tons of mass. The reactor core and electronic systems will be protected using lead-based shielding and insulated bricks made from lunar regolith. To construct these structures, 3D printers capable of utilizing local lunar materials will be critical. China's Chang'e 5 mission in 2020 brought back regolith samples, which are now being used for testing in this very context. To enable robotic assembly and operation of the system, the project includes unmanned control units, automated maintenance arms, insulated power lines, and structural platforms designed to move components during lunar landing. All components are manufactured in modular segments, split into rocket-transportable parts, and engineered for robotic assembly. When combined, including infrastructure, support equipment, and protective systems, the total mass of the entire system is estimated to be between 3,400 and 3,700 tons. This would require approximately 30 to 40 heavy-lift launches to deliver everything to the Moon. According to our hypothetical calculations, which naturally carry a margin of error, transporting just the reactor system using Elon Musk's Starship would cost around $80 million. If done using China or Russia's current launch systems, the cost could rise to $2.6 billion. It's also clear that China and Russia would prefer not to rely on a private company like SpaceX for such a strategic operation. Today, building a similar reactor on Earth would cost around $6.5 billion just for construction. Given the extreme lunar conditions, robotic complexity, and transportation requirements, the cost of installing a reactor on the Moon could approach $10 billion. And since this would be the first attempt of its kind, the added risks and engineering uncertainties could raise the total cost to at least $20 billion. Although most of these operations will run autonomously, sending humans to the Moon will still be necessary. This is where China's Chang'e 8 mission becomes essential, a mission already in progress. Completing this program will require a dedicated human spaceflight budget. While China's exact funding isn't disclosed, we can estimate the cost using NASA's own projection for 2026. NASA has allocated roughly $5 billion annually for this type of mission. Based on China's timeline to complete the project within 5 years, the total human-rated mission cost would be around $25 billion. We're talking about a project of immense scale. According to 2024 data, the combined GDP of Russia and China stands at around $20 trillion. In other words, these two countries could theoretically fund this entire mission by allocating just 0.02% of their annual output. From an economic standpoint, the project appears entirely feasible. Of course, this figure is a rough estimate and subject to correction, but the main point is clear. The endeavor is economically within reach. Now that we've established financial viability, let's explore a deeper question. Why would anyone pursue such a plan in the first place? And perhaps more importantly, what are the technological challenges that must be overcome to make this mission a reality? And are they truly solvable within the next 10 years? First and foremost, we need to develop construction robots capable of operating in low-gravity environments, a massive engineering challenge in itself. Machines designed for Earth conditions simply won't function properly on the Moon, which is only about 16% of Earth's gravity. As a result, AI-driven autonomous construction robots would need to be designed from scratch specifically for lunar conditions. However, even here on Earth, robotic construction systems are still in early stages and have very limited practical deployment. So while reaching this capability within 10 years is theoretically possible, it remains a highly difficult and risky objective in practice. The second major obstacle is the Moon's extreme environment. As mentioned earlier, a full lunar day and night cycle lasts about 28 Earth days, with temperatures ranging from minus 170 degrees Celsius to plus 120 degrees Celsius. Such drastic thermal differences make it essential for the reactor system to rely on radiative cooling. All materials used must be engineered to withstand these conditions. Even a minor crack or deformation could jeopardize the entire system's safety. There's also a critical issue that's often overlooked: lunar dust, or regolith. Lunar dust contains microscopic glass particles and is highly abrasive. During the Apollo missions, this dust caused significant damage to astronaut suits, tools, and even spacecraft systems. Therefore, every robotic system and technical component sent to the moon must be coated or engineered with dust-repellent surfaces or protective layers to mitigate the destructive effects of lunar regolith. When all these factors are taken into account, establishing an autonomous nuclear power plant on the lunar surface requires not just transport and assembly, but simultaneous technological leaps across numerous disciplines, including materials science, artificial intelligence, robotics, thermal engineering, and surface interaction. So, while reaching this level within 10 years is at least theoretically possible, it would only be achievable through massive budgets, international collaboration, and extensive testing programs. In short, the partnership between China and Russia alone may not be enough. Which raises the question, why is such a massive and almost unfathomable investment being made? Is this truly a pursuit of a dream, or something more strategic? In reality, China and Russia aim to show they're not swayed by the short-term, publicity-driven maneuvers of the United States, such as tariffs and political stunts. These two countries have made it abundantly clear they're building a long-term space strategy grounded in scientific and technological cooperation. Another critical point is the legal gray zone. The United Nations Outer Space Treaty, especially the 1979 Moon Agreement, prohibits any single nation from claiming sovereignty over the moon. But neither China nor Russia has signed this agreement, just like the United States. As a result, this project operates in a legally ambiguous area. Because if a nation builds a permanent reactor, base, or infrastructure on the moon, that constitutes de facto sovereignty. The International Lunar Research Station, ILRS, will be built near the moon's south pole and will serve as a permanent base for scientific exploration. Through this station, extensive studies on the moon's geology, physical structure, and natural resource potential will be conducted. At the same time, the base will allow for critical technologies to be tested on the lunar surface, paving the way for future long-duration human missions. China, in particular, is currently one of the world leaders in fusion energy research. To operate fusion reactors, a key isotope is required: helium. This rare isotope is extremely scarce on Earth, but the moon holds it in abundance. Estimates suggest that the upper layers of the moon could contain over 1 million tons of helium-3. Whichever nation gains access to this isotope first may hold an unmatched advantage in a future global energy landscape. And most likely, whoever gets there first wins. Early access to lunar helium-3 could make one nation not just a leader in energy, but a dominant force in geopolitical power as well. If you enjoyed this video, please consider subscribing to our channel and leaving a like. It helps us reach more curious minds like yours. Thank you for watching.